to thank everyone for joining us today at the next talk on the IEEE online forum on climate change technologies. Our next speaker is Professor Matteo Spagnolo. He is a glaciologist at the University of Aberdeen and the director of the Scottish Alliance for Geoscience, Environmental and Society. He obtained his Bachelor in Natural Sciences at the University of Pisa and his master's in remote sensing in Firenze and his geology PhD at the University of Genoa before moving to the UK in 2007. Matteo applies various field, geographic information systems, and remote sensing techniques to the study of glacial landforms. He'll be talking today about a perspective on climate change. Matteo, thank you.
Perfect. Thank you, Charles. Right, so I appreciate I'm probably a little bit different from what you normally get on this forum because I have no background in engineering or physics, and I'm as Charles just mentioned, a geoscientist really. But I hope that nonetheless, providing some context to present-day climate change could be useful. So, yeah. So what I would like to talk today is a little bit about glacier and how they're linked to climate, and what is climate and how do we measure it, and then providing very much a geological overview of climate change, so over the geological timescale, and then moving into the present day and how present day climate change is affecting glaciers and why we care about that. So a little bit about glaciers. So glaciers are iconic. People love glaciers. People want to go visit glaciers wherever possible. Think about Perito Moreno, which is many tourists. It's a big tourist attraction. There are fantastic glaciers in various parts of the world. The Malaspina Glacier in Alaska, for example, is just beautiful, and many more examples. In reality, glaciers cover just about 10% of Earth, but it's a lot of ice out there. And if we were to melt all the ice in one go, we will get pretty much 65 meters of sea level rise. But I don't want to be alarmist here. There's nothing to be worried about, because really, before we melt all the ice on Earth, it's going to take millions of years. So nothing to worry about, but still plenty to worry in a sense, and I'll explain in a minute. So what is a glacier? A glacier essentially is a mass of ice, and glaciers are basically a system where you have an area where you have accumulation of snow, which then turns into ice. So we call it the accumulation area. And then we have an ablation area, which is usually at the margin of a glacier, where essentially the ice is melting. And under its own weight, the mass of ice essentially flow from the accumulation area towards its margin. So in the marginal area, you have a lot of ablation, but there's continuous replenishing of ice that comes from the accumulation area. And the margin could be a water terminating margin. So in this case, there could be ablation as in terms of actual melting or sublimation, but there's a lot of water-related activity and what we call calving, essentially the formation of large iceberg that will then melt once they reach warming condition in the ocean. And the other option is a land terminating glacier, where essentially, as the word says, the glacier will terminate on land. So if we think about land terminating glaciers, which are the ones that I study myself, in a steady state, in a state where the glacier is in balance with climate, you can envision things like in this picture here, where you have the zone of accumulation up high on a valley and the zone of ablation or melting down the valley. But then if we change the climate, if we alter the climate, for example, we go into a cooling period, we will have more snow, and less ablation, and therefore the glacier will grow and advance. On the other hand, if we have a period of warming, we will have less snow over, for example, a year or 10 years time, and more ablation, more melting, and the glacier will shrink, and we say retreat. It's not actually retreating, it's withdrawing, really. And because of the simple relationship between glaciers and climate, we can, in fact, use climate as an archive of, use glaciers as an archive for climate. And we can go back to historical evidence of changes to glacier, and therefore gain information about how the climate has changed, for example, over the past few hundred years. Here's an example of the Muir Glacier in Alaska, and the picture speaks for themselves. This is 1941, this is 2004. So a massive glacier retreat. But we can go farther back in time, and this is really what I work myself the most on. Here you see an alpine glacier, but if you look outside of the glacier, you probably notice in the landscape these features. We call them moraines, and essentially we could look at these features and understand that the glacier used to be larger at some point in the past. But if we can date the time when the glacier deposited this feature, then we can have a sense of how and when the glacier reached this position, and how, again, climate changed since then. And we can go farther back in time, and for example, we could drill inside a glacier, and this happens typically in Antarctica or Greenland. We can extract what we call an ice core, and we can look at the ice core and essentially see how much ice has been accumulating through time. And when we deal with this kind of glacier archive, we can go far back in time, up to 1 million years. So it's a considerable span of time there, and we can see how much ice has been accumulating and melting. And also, very importantly, we can look at the atmospheric composition that is trapped in bubble of air within the ice itself. So very useful archive. But it's not over. We can also see glacier. We can also use glacial deposit, glacial sediment. And with that, we can actually go back to billions of years. So we can go back to almost 3 billion of years ago, the first ever glacial deposit. And in a sense, the presence of a glacial deposit or its absence is giving us an idea of the climate of the past at that time frame. So using glacier and many other climatic proxies, we have been able to reconstruct what happened to climate over the billions and the millions and the hundreds of thousands of years of the Earth history. So perhaps you have heard that the Sahara Desert was not always a desert, right? And here's an example. This is present-day Lake Chad, just a tiny dot here, but just about 10,000 years ago, Lake Chad was a mega lake. As you can see, massive lake. This is a scale down here, 150 kilometers. So we're talking about almost a sea, if you like, a mega lake. And the vegetation surrounding this lake was very much characterized by grassland. There were seasonally flowing rivers and so on. So this was 10,000 years ago. And similarly, you might have heard that now into the millions of years ago, so we're talking about 90 million years ago, Antarctica, which is present day almost entirely ice and very thick ice, up to 2-3 kilometers of ice, 90 million years ago used to be, in fact, ice-free for the most part and covered by a rainforest. So, but what is climate, right? And I think there are different ways of describing and defining climate, but just to keep it very simple, we can think of climate as a system essentially as a system that is redistributing the energy that is receiving from the sun. So you can think of Earth as a heat engine, which is driven by the sun. But because of its shape, the fact that it's an ellipsoid, it's spherical, if you like, or certainly not a 2D body, inevitably the distribution of the sun energy is non evenly distributed across the Earth's surface. So, for example, we all know that the intertropical area will receive more sun energy than the poles, right? So this uneven distribution of energy and heat means that essentially the system, the climatic system, will try to compensate it through a number of atmospheric and oceanic circulation cells and systems and currents and so on. So this is roughly what climate is all about. It's about this redistribution of heat around the Earth. And climate works, climate is affected by a number of forcing, and I'll mention a few in a minute, and is also characterized by a number of feedback mechanisms. So in terms of forcing, just two examples here. This one is very close to me because it has affected the glaciation of the past 2 million years, and it's basically down to the fact that the orbit of the Earth is not constant over time. So what we call eccentricity will change the orbit, will make it more or less circular. The tilt of the Earth axis also varies over time. And there is also the precession phenomenon, which is basically a wobbling of the orientation of the Earth axis. So all these elements means that essentially the energy that the Earth receives, or different part of the Earth receives over time, over the year, over different seasons, will change, and this affects the climate of the Earth. Another example is volcanic forcing. Now we know that volcanoes have an effect on glaciers, but let's ignore that for a second. But if we have a volcanic eruption in the medium to long term, you'll end up having quite a bit of aerosol being produced and in the stratosphere, and that is effectively going to act as a barrier to the sun energy. So it will reflect a fair amount of solar flux back from where it came. And so that will effectively cause a cooling of the Earth. So, for example, one of the largest recent eruption of the Pinatubo in 1991 cooled the Earth, the entire Earth, up to 0.5 degrees for about 3 years. So this is another example of volcanic forcing, but of climate forcing. But there are many others, of course. Just two of them, actually 3 of them. Of course, this is the elephant in the room. This is the greenhouse forcing, and I think probably I don't really need to explain this to you. We all know what this is about, and perhaps a couple of key points about greenhouse forcing. First of all, is that we need it. So there wouldn't be any life on Earth if we didn't have greenhouse gases in our atmosphere. So that's a good thing to some degree. Also, I would like to stress the fact that greenhouse gases are a small percentage of the atmospheric composition. And in fact, within them, the vast majority of it is taken by water vapor. So that's the biggest greenhouse gases, but nobody talk about water vapor, of course, because essentially the life cycle of water is very quick. So, we can increase water vapor. So you wouldn't worry about drying your hair in the morning. Not an issue for me, but because really, whatever you emit comes back to Earth pretty quickly via rain and precipitation and so on. We tend to focus instead a lot on CO2, which is a small percentage of the greenhouse gases, although it's the one that we as human control the most. And the reason is that CO2, unfortunately, has a much longer life cycle. So it takes, up to a few hundred years for CO2 to be completely recycled and redissolved into the ocean once it's been released as a gas. And we do know from empirical evidence that CO2 and temperature are very closely linked. So now about the feedbacks, the climate feedbacks. Again, just a couple of examples. We have positive and negative feedback relative to climate. If we think about a situation where we increase temperature, then you will have more snow and ice melting. And what that means is that as glaciers disappear, as snows melt, as sea ice also melts, you have more darker surfaces revealed on the Earth's surface, and that reduces albedo. So in other words, when you have a very white or light colored surface, a lot of the solar energy will be simply reflected back. But if we have a dark surface, there's a lot of the energy that gets absorbed. So with albedo reduced, we have increased absorption, which leads then to further temperature increase. So this is a classic example of a positive feedback. An example of a negative feedback that perhaps not all of us are familiar with has to do, again, with climate warming. And typically, when you have increased temperature, you also have, at a global scale average, you also have increased precipitation and increased vegetation. And all these together lead to increased chemical weathering of rock. And essentially, this is the, if you like, dissolution of the rock. And you can see this simply by looking at monuments, old monuments. I'm from Italy, so I plenty of example of this where I'm from. You see, for example, here an example where the monuments slowly start to degrade, and that's simply down to the relatively mild acidity of the rain. But if you add to that the increased acidity of the soil and which comes from the vegetation and so on, that could, over time, over very long time, so we're talking about, probably thousands to millions of years, but that will lead to rock essentially weathering. And that weathering means that you'll end up having a lot of CO2 being delivered now as ions, but being delivered to the sea, where essentially trapped by microorganisms into their shells and then deposited at the bottom of the sea. And that is basically a form of carbon sequestration. And that means that there will be less CO2 into the atmosphere, and therefore you'll end up with some level of cooling. So this is the classic negative feedback. Now, how do we measure climate? How we measure? We all know how we measure it, so we use a thermometer, but how far back in time we can use with measurements? That's really the question to ask. And surprisingly, when it comes to temperature, which is the longest climatic parameter ever measured, we only go as far back in time as the 1650, essentially 1660, I think that's when it starts. And in fact, the longest series is here in the UK, in central England. And as you see, naturally there are yearly fluctuations, there are daily fluctuations, there are seasonal fluctuations, there are yearly fluctuations. Remember that when we talk about climate, we're really looking into long-term averages. So really, if I have to look at this graph and think in terms of climate, what I will focus on is the blue line more than anything else. So these are direct climate measurements. If we talk about CO2, which is what climatologists tend to talk a lot about, we can only go as far back as the 1960s, so just less than a century of direct measurements. So how do we know things about like the Sahara Desert or Antarctica? Well, we use climate proxies, and I mentioned the glacier-related ones, but of course there's a lot more than just those ones. Many of these are related to sediments and rocks that we collect from many different parts of the world. So these are all climate proxy data that is available. There are different portals that collect them all, which is fantastic for those of us who study the climate of the past. And as you can see, there's plenty. Many of those are in water, so there are marine sediment at the bottom at the seabed, collected from the seabed and down. But not all of them. There will be also terrestrial ones. So once we have these sediments or these rocks, first of all, we need to date them. Otherwise, we will not know what the climate that we're trying to reconstruct refer to. There are different approaches to dating this sediment. Typically, we tend to use isotopes, more or less radioactive. For example, for the kind of stuff that I do, when I try to date glacial deposits, I will collect rock samples that have been deposited on the surface of the glacial deposit and measure beryllium-10, which accumulates over time as the rock is exposed to cosmic rays. So that's one of the many techniques. But essentially, we have different ways of dating the sediments, the rocks. We could also use the magnetism of the Earth, which has changed over time, over history. So if we have a rock that's formed at a particular time, it will be characterized by a specific magnetic signature. And so we could use that to date the rock. Once we have dated those sediments, then we can look at its content. And through a number of proxies, and I just showed two here, we can then reconstruct the climate. So, for example, these ones are plankton. So these are microorganism that lives in water, and they have a shell, if you like, microscopical one. So you see the scale here. Beautiful, by the way. They're very, they're characterized by beautiful geometries. But regardless of that, these shells might have a content of different isotopic composition ratios that are indicative of the CO2 concentration, of the atmospheric concentration at the time when these shells were deposited. So we can get a sense of what kind of atmosphere we had back then. So with plankton, we can go as far back in time as 45 million years ago. Another example are the density of the stomatal cells, and this comes from fossils of plants. So essentially, if you look at leaves of a plant and under a microscope, you will see that there are some opening, which are these stomata cells, and the amount of opening is proportional to the amount of CO2 that is available into the atmosphere. Why that is the case? Simply put, the plants need the CO2, but also needs the water. And the more opening and the more water will go away from the plant, will evaporate. So when there's a lot of CO2, the plant minimizes the number of stomata cells on its leaf. When there is not a lot of CO2, it requires the CO2, and therefore there will be more stomata. So we can use the density of stomata to understand the CO2 content of the atmosphere at the time when that plant was alive. And now let me go through a little bit of the history of climate change. And first of all, I would like to stress that I'm starting almost from the beginning of the Earth. So we're talking about billions of years ago, and it's a time scale. Pretty much most of the things that I'm going to talk about is a time scale that we cannot fully comprehend. And I've been, as a geologist, effectively, I've been dealing with these time scales for now 30, 40 years of my life, and still largely struggle. right? So just to keep things into perspective, Earth age is 4.5 billion years. Homo sapiens just arrived 300,000 years ago. So if you compare the age of the Earth to a 24-hour, one-day time frame, Homo sapiens is just the last second. Historical knowledge that maybe many of us think they have a sense of, just cover a few thousands of years at best. And really, when we study history at school, for the most part, we talk about a battle, a war, so an event within the historical time frame. We don't really get a sense of that time. So really, when it comes to understanding time for humans, it's mostly about their own memories, their own experience, and at best that's a few decades, right? And really, for many people like me, I can't remember what I did a week ago. So it's just to say that, I'm talking about big numbers here, and it's a struggle perhaps to fully absorb and understand and what this means. But let's give it a go. And I will start with a paradox, right? We're all scientists, so I think we all love queries and quests and complications and paradoxes. So here's one, and it's called the faint young sun paradox. We're talking about really the beginning of the Earth. So essentially for the first 3 billion years, we do know that the sun was expanding. And so for that very long time frame, in fact, the majority of the history of Earth, if you like, the sun shone less than it does today. Initially, it was up to 30% more faintly. And yet, when we look at the geological record, not that we have a lot of, but if you look at the rocks that were formed then, we see no evidence of a frozen Earth, right? If the sun is the primary source of energy for our planet, how come that we had 20-30% less energy coming to Earth and the Earth was not entirely frozen? And what is the thermostat? So there must be a way that Earth was able to cope with this less amount of energy and yet not frozen entirely. And so there are different theories that have been put forward. Possibly there was a lot less land, and maybe there was a lot of volcanism, reduced chemical weathering, and so on. But the reality is that we don't really know what happened there. All we can say is that something was in place because the geological record seems to indicate quite clearly that there was not a widespread frozen Earth at the time. But let's now move into a time scale of hundreds of millions of years. And we look at the past 500 million years, right? So again, we can look at the geological record and at the climate proxies. So let me just touch base on the geological record of this time frame. This is when, for example, we have evidence that there were glaciations, so there were glaciers and large glaciers in Africa, which perhaps comes as a surprise to some of you if you're not familiar with this. How do we know this? Well, if we go present day in front of a glacier and we look at bedrock, we see that there's a lot of striations. You see these lines here. And essentially, these are indicative of the flow of ice over these rocks, because the ice most likely had some rocks trapped inside it. And as it was flowing over the rock, the bedrock, those bits of rock will essentially, by friction, cut the striations. If we go into Africa, into rocks that are as old as several 100 million years, we do find the same kind of striation. So that's an indication that those rocks were once in front of a glacier. If we go to Antarctica, not for the same exact time, but within this time frame of the past 500 million years, If we go to Antarctica and we look at the fossils that we find in some of the rocks that are exposed, that are outcropping in Antarctica, we recognize that there are species of plants that are typical of rainforest. So again, this is an indication that Antarctica at the time was not covered in ice, and instead was very much a vegetated continent. So, and then if we actually add a number of proxies that are available, they come with a large level of uncertainty in terms of what they can tell us about climate. And you see that from now on, I will always refer to CO2 concentration. So here's the past 500 million years, which, by the way, is only 10% of our Earth history. But 500 million years, and you see where we are present day with relation to CO2, high uncertainty in what we see here, but we do have a number of proxies that show a consistent story, all in all. And the story is that there has been a lot of fluctuations. So climate has changed quite a bit. Some of these changes, for example, here around 250 million years ago, were linked to dramatic mass extinctions. So about 95% of all living species disappear around this time. This is not the dinosaur one, which is far smaller, but you know, it's clear that climate was somewhat controlling the evolution of life. So really, paleoclimatologists will describe this as a period characterized by what they call icehouse or greenhouse state. So icehouse, essentially, most of the Earth was covered in ice, and greenhouse, most of the Earth was ice-free and covered, most likely in vegetation. So what was controlling climate at this time scale? Paleoclimatologists believe that it's tectonic for the most part. So to some extent, this is down to the fact that tectonic control the distribution of land. And so, for example, when we see evidence of glaciation in Northern Africa, including in the Sahara Desert, that's not where Northern Africa was at the time. Northern Africa was at the South Pole 450 million years ago. So some of the evidence, especially the geological evidence, can be explained simply by the land distribution, which changed over time because of tectonic. But that is not enough to explain, the level of climate changes that this plot shows. And to fully explain that, we really need to go down to a mechanism that was controlling CO2 at this kind of time frame. And what is believed is that for the most part, this was controlled by the speed of spreading of the ocean. So plate tectonic, you know that the upper portion of the Earth essentially moves. It moves at a fingernail growth speed. So you barely see it except when you have an earthquake. But when you multiply that into the million of years, there's enough movement to change the face of the continents and their size and so on. And that growth, that change was not constant. So there were times when ocean spreading was faster, and at that time, essentially, we had more CO2 that was coming out of the opening of the ocean itself. And then as continents migrated away from the opening of the oceans and they collide against other bits of continental crust, they were causing a lot of volcanism, which in turn was also releasing quite a lot of CO2. So a lot of CO2 into the atmosphere essentially then meant warming, and this is how we explain the greenhouse climate of the time. And then when the ocean spreading slowed down, we were under icehouse climate conditions. But let's now move into the 5 million year time scale, and we look at the past 50 million years. So uncertainty are now reduced. We have a lot more proxies, or more proxies maybe, And most of them consistently point to a similar trend. And the trend is very much that of cooling. So for the past 50 million years, the Earth has been cooling. Why is that? Paleoclimatology have discussed this endlessly. Initially, they were thinking that this was down to the fact that some major gateways opened. So, for example, Panama, the Drake's Passage, but that was then proved not to be the case. They couldn't really explain what we were seeing. In other scenarios, people simply realize, well, most of the mountains that we see around us comes from about this time frame. So maybe it has to do with the fact that with a lot of mountains, there's a lot of rocks exposed to weathering, and therefore more CO2 is trapped and it's cooling. That's not quite entirely true, because mountains building probably was always happening even before the past 50 million years. But what they think is the main reason for this almost continuous cooling over the past 50 million years is not just the building of the mountain per se, but it's the building of a very large area of high elevated terrain. And that's when essentially the India plate collided with the Asian plate and formed the Himalayas. But it's not just the mountain itself, not just the Himalaya itself that matters here. It's more the fact that behind the Himalaya, north of the Himalaya, the Tibetan plateau was formed. And this is a massive amount of land, mostly bare land, so rock essentially exposed to weather, and which has been weathering for many million years now. And we can see this in the amount of CO2 that is, well, not CO2, but in a sense, CO2 that is trapped in the sediment in the seas that drains this area. Let's now move to the 50,000 years time scale, and we look at the past 3 million years. So this is coming closer to what I look at when I study my glaciers. So very, very important, of course, improvement in quantity and quality of data. Climate continued to cool up until about 1 million years ago. And then from that point onwards, we had regular fluctuations of what we call glacial and interglacial period. This is a time when we also have probably what climatologists consider the best climatic proxy ever, which is the oxygen isotope, is the ratio between O16 and O18 found in marine microorganism shells. What does it tell us? Well, essentially, evaporation so that there is an amount of oxygen 18 and 16 in the seawater, but evaporation will, of course, preferentially evaporate the lighter O16. In a normal condition, this will then eventually come back through precipitation and runoff, come back to the oceans. But if it is cold, then what happens is that the O16 is trapped in ice that is growing on the continents. And so the seawater composition starts being depleted in O16, and the ratio between O18 and O16 then becomes progressively higher, so more O18 than O16 during glacial conditions. So if we look at the past 500,000 years here, you see that we have this alternation between times where we had glaciations, effectively, what they call here ice age, and times where we have what we call interglacial. These are a completely different time scale than the ice house and the greenhouse states that I talked earlier. But nonetheless, we had these oscillations for pretty much the past 1 and almost 2 million years. And this is almost entirely driven by the orbital forcing that I described at the beginning of this talk. So during the glaciation period, we will have pretty much most or a large part of North America and Northern Europe covered by ice sheets. And during interglacial, the ice would have been completely disappeared. We can then move into the past maybe 20,000 years. And we are now looking at the last glaciation, which essentially culminated around that time, around 20,000 years ago. We can now, as you see, we can now look at actual temperature rather than CO2, because it's very easy to convert the delta weighting signals into temperature. So since the last glacial maximum, as we call it, of course, there's been warming, and this has been probably the most dramatic warming that we have evidence of. And between essentially 18,000 years ago and 10,000 years ago, temperature increased by about 5 degrees over 5,000 years. So a peak rate of 1.5 degrees per 1,000 years. So pretty dramatic relative to the longer history of climate change. And around 10,000 years is when we most likely entered the last interglacial period. And it's an interesting time frame, the last 10,000 years, because we had a peak of relatively high temperature around 6,000 years ago. And this is also the time when humans started to develop agriculture fully. So many argue that there is a link between this warming and the full development of agriculture. And then from about that time onward, temperature started to decrease. So for many scientists, this is probably the beginning of the natural cycle that will eventually lead towards the next glaciation. And temperature continued to decrease until about 1850. And then things changed again. How do they change? Now we have actually direct measurements, and we all know that essentially from 1900 onwards, temperature started to increase quite dramatically again. Now, I don't think I need to explain too much about this, but just in a few words, we know that we have increased, since then, we have increased our emission of CO2 and other greenhouse gases. We do have measurements of these gases in the atmosphere that match with our emission measurements. We have models that suggest how much these emissions will convert into increased temperature, and unfortunately, we have measurements of increased temperature that match exactly those model simulations. So that's where we are now, and if we want to put this into a little bit of perspective, I'm not sure whether it's useful or not, bear in mind that these are different time scales, but essentially where we are now is in terms of temperature relative to the pre-industrial time, so relative to the temperature of 1850 to 1900, we are about 1.5 degrees warmer, and we are not far from the highest peak of the interglacial of the past 100,000 years. And if we look at a different scenario of where temperature might go in the future, it's very much possible that we'll reach temperature of that are comparable to what we had millions of years ago. So how is this climate change different from all the climate changes that we discussed before? The IPCC report, which is compiled by a number of scientists, mostly climatologists, will focus on 4 aspects. They will say that it's warming almost everywhere. And for the past 2,000 years, this is unusual. There has been warming, but it was not experienced everywhere. It's warming very rapidly, and personally, I think this is the scariest bit. The warming is reversing a long-term cooling, as we saw, from about 6,000 years ago, temperature has been cooling, and this is definitely reversing that trend. And it has been a long time since it has been this warm, at least 125,000 years ago, well, at least 6,000 years ago, but we're now leading towards temperature that were typical of 125,000 years ago. I will say that if we compare this to the increasing temperature that we had from the last glacial maximum to the beginning of the interglacial, that was about 1.5 degrees Celsius over 1,000 years. And where we are now is at 1.5 degrees Celsius of increased temperature over a period of 125 years. So it's a magnitude of difference. Sometimes these plots do not show this at all because they're different time scales, but really is dramatic. And one might say, well, perhaps we experienced similar warming before, we just didn't have the right resolution to see that. That's possible, to be fair. And what we know, though, is that for the past 2,000 years, certainly we had the resolution, and what we see recently is absolutely unprecedented. And I will say that, what the history of climate tells us is that there are negative feedback in place, and probably in the long term, this will kick off. They probably already started to kick off, and eventually will control the warming, will limit the warming. But those most likely operate at a time scale that is orders of magnitude larger than the anthropogenic climate forcing. So finally, the last few slides, I would like to go back to the beginning of the talk and see what this present-day climate warming is doing to the cryosphere, to the ice and snow of our planet. So ice, of course, and snow are melting, which is inevitable when you warm the climate. But what does it mean exactly? Well, first of all, glaciers are disappearing, and perhaps in a bit of a folkloristic way, you might have heard of the news of people in Iceland and in the Alps holding funerals for the disappearance of the glacier. And, that's kind of a community feeling about, a feature that perhaps was part of their life that is now gone. And it is important, but there are much more serious and important consequences than that. So I was recently part of a paper that got published in Science, where we demonstrated, for example, that the retreating of glacier in Greenland is essentially leading to instability, and in this case, basically half of the mountain collapsed because the glacier, which used to put pressure against the valley flanks, have gone. Now the mountain collapsed into a fjord and creates tsunami that it was, something like 200-meter high. So these things are happening in places like Greenland, luckily where very few people live. But they're also happening, for example, in the Himalayas, and you might have heard of the Chamoli disaster, which killed several hundred people, and so on. So this is one of the issues. The other issue is that as glaciers disappear, that affect the amount of water that is available, for example, for agriculture. It means that initially, as glacier retreat, there will be and melt, there will be a lot more water and perhaps a lot of more flooding than we were expecting otherwise. And then eventually, once they're gone, there will be a lot less water. And also it means that if we had melting typically in the summer, when it tends to be arid in a specific region. And so the melting of the glacier in the summer was actually providing water at a period of seasonal aridity. Now that the glacier are gone, of course, that becomes pure aridity, and means that it's difficult to cultivate anything. As the ice is melting, and in fact, as the global ocean heats and expands, of course, one of the consequences is that the sea level is increasing, and that combined with weather, weather events like typhoons and so on, will essentially cause and is causing a lot of coastal erosion, which is a problem for many of the coastal cities and countries and lands that perhaps some of us live in. It also means that permafrost is reducing, so the permanently frozen part of the Earth, which actually trap a lot of methane gas, which is another greenhouse gas, is disappearing, and so this releases a lot of additional greenhouse gas, so positive feedback. which is certainly no good. And perhaps the most dramatic change, well, a change is in the reduction of overall snow across the globe, but really perhaps the most dramatic change is on the sea ice. Sea ice has been changing at a terrible fast rate, and you probably heard that this is becoming a geopolitical issues because it's opening up new ways of for transport in the Arctic and so on. But regardless, the point here is that as sea ice is disappearing, and it is disappearing really fast, that reduces albedo, as I said at the beginning, which is another positive feedback. And it's no surprise that the Arctic present day is warming up almost 3-4 times faster than the rest of the Earth. So globally, we are at 1.5 degrees Celsius above pre-industrial. The Arctic is almost 4 degrees Celsius above pre-industrial, so it's pretty shocking. So to conclude, we have glaciers and we have many other proxies that tell us about the climate of the past. We do see the climate has changed quite dramatically and many times over different time series, steps. We know and we see evidence that there has been different climate forcing and different feedback mechanisms, including thermostats, so mechanisms that are negative feedbacks that are able to contain and limit a directional travel. So if it's warming, it will stop the warming or limit the warming. If it's cooling, it will do the opposite. We unfortunately see evidence that recent anthropogenic, so human-induced warming rate is very much unprecedented. That is having a dramatic effect on the cryosphere, which has then, unfortunately, many negative consequences for humans. And perhaps if we want to learn a lesson from the history of the climate of the past, is that climate has changed, but the planet has natural ways of dealing with that. So it has natural negative feedbacks. And I think these are acting already, and they will continue to act. And so it's not that the Earth will continue to warm endlessly and it will be the end of life on Earth. But the problem is that most of these feedbacks, as far as we know, operate at a much longer time scale than the current warming. And I will leave it there. Thank you very much.
Well, Matteo, that was very interesting. Thank you very much. We have a few questions. One of the questions was about how you mentioned that new trade routes are opening. When I was a kid, the search for the Northwest Passage was a big story, but it looks like today the Northwest Passage works. The question is, should shipping industry use these new routes instead of trying to preserve the glacial area of the Arctic?
I will say that the transportation routes have relatively minimal effect on the sea ice itself, and so in a sense, I see no problem with them using these new routes opening. Ideally, we don't want them to open. We would like them to be sea ice covered. So the least disturbance that we do to sea ice, the better. But if the sea ice has disappeared or is disappearing, so I don't see an issue with using them, except that there are other side effects, including geopolitical and the consequences for the local communities that live nearby that should be taken into consideration. So it feels a little bit like Far West at the moment, what's happening with Arctic transportation. Yeah, I think I will say that, we shouldn't necessarily focus on that. We should try to focus more on what is causing the sea ice disappearance and see whether we can do anything about that as a primary goal. Then, of course, there are other arguments that are important too, and could be more specific about, leave that regions as untouched and undisturbed as possible.
Okay. This is a question for myself. A frequent comment is that climate change is not happening because some glaciers are growing. Do you have a comment about this statement?
Yeah, so we have data pretty much about every single glaciers in the world, and we see that I cannot provide an exact number, but the vast majority, probably 90% of the glaciers are unfortunately retreating, and some have disappeared. Many have disappeared already. There are some exceptions, which is worth considering, and those are glaciers that are not linked to climate for a reason or another. So, for example, if you have a glacier that is debris covered, so covered in a relatively thick layer of debris, so rocks, fragments, that essentially create an insulation between the atmosphere and the glacier. So the glacier doesn't really feel what's happening above it, if you like. And so that insulation works by limiting the glacier retreat, not necessarily making it advancing, but certainly limiting its melting, if you like. Another exception is are glaciers that sits on volcanoes where there's a lot of geothermal heat. So that is doing the opposite, is actually accelerating the glacier retreat much faster than climate will naturally do. But the few cases where a glacier is advancing, we call them surging glacier, that is down to essentially a relatively complex mechanism of instability within the glacier itself, where basically the glacier is quiescent, so quiet, keep building mass over a period of time, and then all of a sudden it releases the mass by flowing really fast and advancing. But as it flows and advances, actually is thinning. So if you look at the mass of the ice over time, you're not really gaining anything. It's just a flowing mechanism, an instability within the flowing mechanism itself. So yeah, those are real. There are glaciers that are advancing, but not because of climate.
Okay, that was actually very helpful for the next time I talk to a NIMBY. I'm going to paraphrase a question. You focused mainly on just CO2, but there are other greenhouse gases, in particular methane. Do you think that focus on CO2 is good enough, or should we be focusing on other gases?
So I think we should focus on all greenhouse gases for sure. It's easier to focus on CO2 because the link between CO2 and temperature is very clear, and most of the proxies that we look at for the past are very much able to quantify CO2 and not necessarily other gases. And that's why, the major focus, and also perhaps the most important point of all is that of all the greenhouse gases that we emit, CO2 is the biggest one. Having said that, of course, other greenhouse gases are very important. I will not spend a word on water vapor, because I don't think that's really particularly relevant. Though we do see, with increased temperature, we do see an increase in water vapor. But as I said, the cycle is fast enough that it doesn't affect temperature so much. Other gases are absolutely important. Methane is one of them. You probably heard about, at least in Europe these days, in the past couple of days, there's been a big discussion about this new product that is given to cows to reduce the amount of methane emissions, and whether or not it's safe for humans and so on. But so clearly, people are looking into ways of reducing methane emission. Methane is a small portion of the greenhouse gases, smaller than CO2. And as I said, we contribute a lot less methane to the atmosphere, but nonetheless is a lot more powerful, right? So there's also this aspect to consider. CO2 has an impact on temperature, methane has a much bigger impact on temperature, so we should absolutely care about it. And what's worrying about methane is permafrost, from my point of view as a glaciologist. So permafrost, what I mentioned earlier, there's a lot of methane trapped in permafrost, so effectively is stored there, and unless we release it, is doing no harm whatsoever. But unfortunately, with the melting of the permafrost, then a lot of that methane is emitted. And then, of course, the other big issue with methane is animal and cows and so on. So that's why you probably heard the importance, according to climate activists, of changing diet and so on.
Okay. Well, that's very good. I want to thank you for a very interesting presentation, and we hope to get it posted in a few days.
Perfect.
Have a great day.
Thank you. Thank you for this opportunity. Bye, Charles. Bye, everyone.
Thank you, Matteo.
Okay. Well, we'll be here tomorrow with talks. Thank you.